All right, so we're recording now. Again, I just want to repeat that we are going to go over this discussion section. And if you guys at any point feel like, no, I don't understand what's going on these slides, please stop and ask questions. And if still it doesn't make sense, we can go over it on my iPad. You can interrupt me anytime and say, oh, this is not making sense to me. Please, write it down on your iPad and explain. So I can write and explain, okay? All right. So now we're going to go over a couple questions. These are the specific questions, the quiz questions that you guys, like not all of you, most of you got wrong. So let's look at the homework quiz 4, question number 2. So we have, the question was, computer adaptive tests are designed to adjust their level of difficulty based on the responses provided, to match the knowledge and ability of a test taker. If a student gives a wrong answer, the computer follows up with an easier question. If the student answers correctly, the next question will be more difficult. Let Z be the number of questions a student answers correctly before they miss one during a computer adaptive test. What type of distribution does Z follow? Geometric, Bernoulli, binomial, or none of these? What do you think? Anyone? You can speak up or you can type it. Okay, I have a vote for geometric. I have a lot for geometric. Okay, can one of you tell me why do you think it's geometric? Okay, I have one vote for none and few votes for geometric. Okay. Anyone, can anyone explain their answers? Because it's number of times until a success. Okay, so let's read this carefully. Let Z be the number of questions a student answers correctly before they miss one during the computer adaptive test. Yes, but also, that's definitely what, yes. But also let's reread the question. The computer adaptive tests are designed to adjust their level of difficulty based on the responses provided to match the knowledge and ability of a test maker. If a student gives a wrong answer, the computer follows up with an easier one. And if the student answers it correctly, the next question will be more difficult. So I think Austin was the one to say none of the above. Yeah, I think, yeah. Austin was the one to say none of the above. And Austin, you are correct. It is none of the above because the difficulty of the question depends on what the previous answer was, right? Was it correct or was it not? It changes. The level of difficulty changes, which is over time, it depends on whether the student answered the previous question correctly or not, right? It changes over time. That's why it's none of the above distributions. Does that make sense? Any questions?
This is just, I kind of understand it. This is just more of a general question. What if like the question said, instead of like it changes like from like easier to harder, what if it was to say like it like continually gets harder or it like continually gets easier? Would that change the type of distribution, or would it still also be none?
It would change. Also, it depends on what options you're given, right?
Yeah, okay.
There are these nitty-gritty details that you need to be very sure about questions, right? And also it depends on what options you're given. Okay. I will follow geometric since it got more. So we have a question in the chat. Let's see. I thought I would follow geometric since it got more difficult as it grew, meaning less test takers would reach more questions. Okay. So we are okay, I'm just going to explain this once again. So here Z, which is a random variable here, denotes the number of questions a student answers correctly before they miss one during a computer adaptive test. So let's say if I'm taking a test and I got the first question wrong, the next question is going to be easier. Let's say I got that one wrong as well, right? But what Z denotes is the number of questions student answers correctly. In my case, it would say zero questions answered correctly, right? Before. So number of questions student answers correctly before they miss one. I missed the first one, so Z is 0. But if someone misses like the 10th one, so it will be 9. But we can't predict the pattern right now. It's not geometric because we cannot predict a pattern. There's no pattern to this, right? Does that make sense? Cameron? Maybe? Yeah. Okay. Anyone else? Any questions so far? Okay. Should I move on to the next one? Hopefully? Yeah? Okay. All right. Let's go to the next one. So next is that we have an urn which has 5 balls numbered 1 through 5. Okay. We are randomly picking a ball and recording its number and then putting it back. So what does that mean? If we are taking a ball, recording what it was, and then putting it back. What's happening? Is the urn replacement? Perfect.
Yeah.
Yes, thank you. Thank you, guys. We are sampling with replacement. Now let's take X, which denotes the sum of 3 numbers you recorded, because what we are doing is we are doing the same operation 2 more times. So total 3 times. So we denoted 3 numbers. We have 3 numbers. And then X is denoting the sum of these 3 numbers we recorded. We want to find the probability that X is greater than or equal to 12. What do you think? I don't want you to solve it. It's okay. Just tell me what you guys think. Any ideas of what we should do or what's happening here? Any ideas? No ideas? Is there something in the chat that I maybe missed? For this one, I just drew table of sums. That's really good. Find the probability of getting 12, 13, 14, or 15. That's perfect. We could draw all good responses. So what we're gonna do is, since it's gonna be a big table if we do everything, we're just gonna make a table for when X becomes 12 or greater, as in 12, 13, 14, or 15. Okay, so let's see. Also, before we do that, what is the let's see, what is the total number of options that we should have? How many total outcomes can we have for this problem? Anyone? Yes, thank you. 5 cubed to 125. Okay, so we should have these many observations in our sample space. Now let's make a table. So what does the table show? Now we can have 12 going till 15 and some of those 3. So ball 1, ball 2, ball 3. So let's say we get 5 for the ball 1, and since it's with replacement, so our ball 2 can also be 5 and our ball 3 can also be 5. So the sum of that can be 15. Or we just keep decreasing the last one and then try to make all these combinations until we get to the last one for 12. So these on the right side are all the combinations that would give us 12. We don't need anything that would give us below 12. And then these are the combinations 13 to 15. So the total number of combinations, if you look at, is 20, right? So for the probability, we'll just divide 20 by 125, and this will be our answer. Any questions? No questions? Is everyone clear? Clear? Thanks for affirming that it's clear. Anyone else? Any questions before I move? No? Okay. Wait, how did you get 20? Okay, good question. So all these outcomes, we just made a table where our x, which is the sum of the three balls, should be greater than or equal to 12. So if you count these outcomes, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So there are 20 ways we can get x to be greater than or equal to 12. Okay, does that make sense? How would you do this without a table? Is there an equation? This is the easiest way. There's no equation for this unless you want to do it in your head. You just have to try making the combinations and looking at it. Okay. Yeah, okay. All right, the next one is a little tricky, but not too difficult. Let's see. We have 25 people in a room. 10 of them like ice cream, 8 of them like fried chicken, 5 of them like both. A person is selected at random. What is the probability that the person selected likes neither ice cream nor fried chicken? What are we trying to find here? Any ideas? I used it. Yes, perfect. Venn diagram is a really good way to go. Weight table, okay. So should we go over it? Or can anyone tell me, what are we trying to find here? Let's see, in this case, what I'm gonna do is I'm actually gonna share, if I can, my iPad. Yes, good news. Neither ice cream nor fried chicken. We're going to try to find the probability of that. Yes, absolutely. I'm going to try to share my iPad. And let's talk about this question a little bit. Okay. Can everyone see my iPad? Not, let's see. Oh, there we go. Yes, okay, perfect, thank you. All right, so let's see. The total people we have is how many? Anyone? 25, good, thank you. And then we have people who like ice cream, that I'm just gonna say ice cream. We have how many? 10, thank you. And then we have fried chicken, that is 8. Okay, thank you, Jamie. All right. Now there are both, which is 5. Thank you, Rihanna. Okay. So now what are we gonna do is, let's make a Venn diagram, if I can. Okay. And let's try another one. Okay. So let's denote this one to be ice cream. This one to be fried chicken. Okay. Now that means that total for ice cream we have 10. So we have 10 people over here. Okay. Then we have 8 for fried chicken. So we have 8 people over here. And then we also have both has 5. So where should 5 go? Any ideas? Where should this 5 go? In the middle. Perfect. Thank you. Thank you, guys. So here. So if I want to just shade these areas, so 5 has this area. So both. And then 8 covers this and its own here. Okay. That's our fried chicken. And then we also have our ice cream, which covers this whole, including the middle part. Okay. All right. So I want to find the probability that a person who is selected likes neither ice cream nor fried chicken. How should I go about it? First, tell me, what does this area represent? Okay. That's, yes, both. In statistical terms, this represents A intersection B. Both ice cream and fried chicken, yes. So this represents A intersection B. Okay. A intersection means I like both. And then what if I want to say I like either ice cream or fried chicken? How would I represent that? If someone likes ice cream or fried chicken? A union B, perfect. So A union B should be this part. Is that clear? Any questions so far? Okay, I'm gonna give you guys a second to just absorb what I just said and this Venn diagram. Is that okay? Should we continue? Anyone? Yes? Okay. So that means that what we want to find is, we want to find neither. So no, not ice cream or fried chicken. What should we do to get that? What do we want to get at? What do we want to get at when we say neither? What do we want to find in statistical terms?
Is that the complement of?
Yes.
Okay.
Of what?
Of A or B.
Yes, perfect. So this is A or B. We want to find neither. So that should be the A union B complement. But technically we want to find the probability, but that's another technicality. But does that make sense what we want to find? What probability we want to find of?
Yeah,
okay,
makes sense.
Perfect. Thank you, Justin, for helping us out. All right, so now I'm gonna stop this share. And I'm gonna share the slides again and see if you guys get that. So now what they're saying is 5 people like both ice cream and fried chicken. So 5 people belong into A intersection B, as I showed you. Then 10 people like ice cream, right? So 10 minus 5, that's 5 people in A intersection B complement. So what is the B complement? So here what they're taking is A is denoting the ice cream, B is denoting the fried chicken. So what should be B complement? If B is the people who like fried chicken, then what should be B complement? Just in words, what is B complement? If B is the set of people who like fried chicken.
Those who don't like fried chicken.
Perfect. Thanks, Jarman. Thanks, Justin. People who do not like fried chicken. So if I intersect that with A, which is people who like ice cream, that's just the people who like ice cream, right? Is that clear? Yeah. Okay. Similarly, we can find 8. So we know 8 people like fried chicken. So 8 minus 5, 3 people belong to B intersection A complement, right? So that means 25 or we have total people. If we subtract the people who belong to this category and who belong to this category and who belong to A intersection B, we will get the number of people in A union B complement. So that's 12 people. And since we are finding the probability and not just the number of people, we divide by the total people present in the room, which is 25. Does that make sense? Let's look at the diagram again here. So we have 5 people over here, and then 5 people over here, and so what's going on in here is this is just the 5 people who just like ice cream, like right here, right? What I showed you, the 10 was total of that. 5 people who just like ice cream, 5 people who just who like both, and 3 people who just like fried chicken. And then we add them up and we subtract from total, that would be 12. Does that make sense? Yes, perfect. Thank you. All right. So there are a few notes. There were other questions some people got wrong. There were like video quiz 2, question 4, and that is very similar to the fifth video in the video list 1. Then homework quiz 3, question 3 is identical to problem 4B in homework 3, and also to the third example in lecture 9. So she said that you guys didn't go over through this example, but she asked the students to go over the solutions and steps given in the lecture slides on their own. So it was pretty similar to that. And I am going to stop recording now. Any questions before I do? Okay.